Good morning, students. Welcome to Commutative Algebra lectures. In this lecture, we'll discuss about exact sequence and their properties. Okay, let's let's start with a definition of what is meant by an exact sequence. So consider MIs, okay, which are A modules, and FIs are mapped from module homomorphism from MI minus 1 to MI. Okay, then if you have a sequence, this mi minus 1 to mi to mi plus 1 and so on, then is sequence of module homomorphisms is said to be exact at mi. Okay, so this sequence is exact at given module mi if you take the image of this fi. Okay, that means image of fi. Okay, we know image of fi is a submodule of this mi, and you take the kernel of fi plus 1. We know it is also a submodule of mi. These two should be equal. Then we say that the sequence is exact at mi. Okay, and if this is true at every mi, then we say that the sequence itself is exact. Okay, fine. Let's see quickly some examples. So if you take some examples, take n submodule of m. This is submodule. Then obviously we can have from 0 to n, obviously map sending 0. Okay, then because it is a submodule, you can have an inclusion map. If you call it, this is f prime and this is f, right, where obviously it is an inclusion map sending x to x itself, right. Then you can check that it is a exact, right. Why this sequence is exact? Because what is here, the kernel of f is nothing but 0. There's only one element goes, and this is same as image of f prime because we are having only one element here, right. So that shows that this is an exact sequence. Okay, because if you observe, there is nothing here. Okay, what is here is this one, right, and kernel of f we require should be 0. So not only this one, if you take f injective map, then 0 to n, n to m, if that f is injective, then it will become a exact sequence, right. And not only this, because n is a submodule of m, so you can talk about m modulo n. Okay, so if you can talk about m modulo n, then m to m modulo n, we have a natural map, then to 0 sending everything to 0. So if you call it, this is g and g prime, right, sending x to x bar, you can check that this is also exact. Because what is image of g? Image of g is, because every element is going here, so it is nothing but m modulo n, right. Then it is same as kernel of g prime because we are sending everything to 0, right. So therefore this is also, so when once n is a submodule of m, then we have two exact sequences, n to m, okay, 0 0 to n, n to m, then m to m modulo n, m modulo n to 0, right. Not only that, as I said already, you can generalize this. So if you take 0 to m prime to m, okay, if you take a map, this is exact if and only if, what should be the condition, we want this kernel f should be 0, so therefore f is injective. Okay, similarly m you can call it to m double prime to 0, okay, is exact if you call it this as g, then if and only if g is surjective map. Okay, right, you can check that if g is surjective. Fine. Now we have this concept of short exact sequence, okay, which is very useful many times. So a sequence of the form 0 to m prime to m prime to m double prime to 0. Okay, so it is like basically you have three, okay, modules, right, f and g. Then we say that this is called short exact sequence. Short exact sequence if this it is same as like whatever we have earlier. If you consider this much part, when this will be exact at m prime if f is injective. So therefore the condition is f is injective. Similarly, if you consider this part, this much part, then when this will be exact if G is surjective. Okay, and when you talk about this exactness at M, then it should be image of F is same as kernel of G. Okay, if these three conditions are satisfied, then we say that such a sequence is short exact sequence. Okay, right? Okay, so this you can, of course you can write this if G is surjective and all those things. G is surjective is same as saying that M modulo F of M prime. M modulo F of M prime is isomorphic to M double prime, but this is same as co-kernel of F, which is it should be isomorphic to M double. Okay, this short exact sequence are useful. One can have, why they are useful, that every long exact sequence actually can be split into short exact sequences. Namely, if you take this long exact sequence mi minus 1 to mi to mi plus 1, then you have 0 to ni and ni to mi. Okay, mi to ni plus 1. So you take mi minus 1 to mi. Okay, then mi to mi plus 1. This is fi and fi plus 1. Okay, and so on. How we can get a short exact sequence from here is 0 to ni. What is ni? We want this should be image of fi. Okay, so you take image of fi, which is a submodule of mi, right? Because if we know something submodule, then from here to here we have a map, right? So that means ni we are considering as image of fi. We know it is a submodule of mi, so therefore from here to here we have a map, right? Then of course we can take image of fi. R is same as kernel of fi plus 1, there is no problem. And this mi to similarly ni plus 1, ni plus 1 you take it as image of fi plus 1. Okay, image of fi plus 1, then to 0. You can check that it is an exact sequence. So if you want to check that it is an exact sequence, if we call it this is phi and this is psi, what we want to make sure that phi is injective. That is very clear because the map, this is an inclusion map, so it is clearly injective, right? And we want to show that this psi is surjective, and that is obvious because this image of fi plus 1, right? If you take anything that should come from mi, and using this exactness property, you can check that image of this fi, whatever you are having here, image of fi is kernel of fi plus 1 and so on. So it follows from there, right? If something goes to 0, it should come from here. Okay, fine. So that is an inclusion map. Then this phi mi map from ni plus 1, it is simply fi plus 1 of x is surjective, right? And you can also show that mi upon kernel of f phi I is isomorphic to ni plus 1. So therefore, you have here kernel of phi, then mi modulo kernel of phi, right? That it will become exact sequence. And you can check that this is precisely ni, right? So any long exact sequence can be uh, split into short exact sequence. Namely, you can write here. So this mi, so mi you take first one you take ni, which is same as phi. So if you take phi, which is an inclusion map, okay, ni is image of fi, right? Now we will prove an interesting result about exact sequence. Okay, we can construct, suppose you take m prime to u, sorry, m prime m prime to m. Okay, I think this one, m prime to m, m to m double prime to 0. You call it this as u, and this is v, right? Not v bar, it is v to 0. Suppose this is a sequence of, you have a sequence of module homomorphism, then this is exact, this sequence is exact if and only if you take any module n, n is an a module such that 0, the sequence, the following sequence, 0 to home m double prime to n, then home m comma n, home m double prime, sorry, this m prime to n, this should be exact. That means this is in reverse order, right? So let me repeat again. Whenever the sequence m prime to m to m double prime to 0 is exact if and only if you take any n a module, then the applying functor 0 to home m double prime to n, that means from here you are getting, when you apply, then you get 0 for this home. That should be exact. So what we'll prove here is, suppose we will assume that this is exact, then we will prove for any n module this is exact. And when you consider such thing for any n module, if this is exact, we will prove that this is exact. Okay, fine. So proof is not a difficult one. uh, it is like most of the time we want to trace the diagrams and we should understand u v. This, if you call it this is u bar, you can call it this is u bar, this one is v bar, and this one is u bar. Okay, fine. So suppose consider this quickly, m prime to u, some m prime to m to m double prime to 0. This is u and this is v. Suppose this is exact. What is meant by saying that this is exact? This v is whatever you have here, v is surjective. We don't know whether u is injective or not because you don't have 0 here, right? It is not short exact sequence. So v is surjective, and image of at m means what? Image of u should be same as kernel of v. These two conditions we know. Using these two conditions, we want to prove that, we want to show that v bar is injective, because what is our sequence? This is our sequence. We want to show that this is exact. That means we want to show that this one, whatever we have v bar, this is injective, and image of v bar is, image of this v bar is kernel of u bar, like, okay, image of v bar. So what is our claim? Our claim is to show that this v bar is injective. Okay, that is first claim. Then the second one will show that image of v bar is same as kernel of u bar. Okay, fine. How we will show that v bar is injective? What is meant by saying that v bar is injective? Suppose assume v bar, remember v bar is a map from where to where, then it is easy to understand. V bar is a map from home m double prime comma n, home m double prime comma n to home m prime comma n. This is our v bar. Okay, fine. So this is m comma n, not m double prime, m prime, it is m. Okay, so you take this one. Now suppose v bar of f is 0 for some f, then we want to show that that f is actually 0, right? Where f is what? F is an element here, that means it is a homomorphism from m double prime to n. But how v bar of f is defined? It is same as f composed v, it is equal to 0, right? So f composed v is a map from where to where? Because v is a map from v, you can check here, v is a map from m to m double prime. So then m double prime to n, so you get this is actually a map from where f composed v is a map from m to n, right? What is meant by saying that this is a 0 map? Any element if you take on x belongs to m, it is 0. So that means f composed v and entire m is actually a 0, right? But that is same as saying that this f of v of m is 0, but v is given to be surjective, so v of m is same as m double prime, right? Therefore f of double prime is 0. That means f is 0 on m double prime. That shows that f is actually 0, right? So therefore v bar is injective. Okay, now let's show that image of v bar is same as kernel of u bar. If we want to say that two sides are equal, you show that one is contained in the other, right? And the other way, kernel of u bar is contained in image of v bar. What is meant by saying that image of v bar is contained in kernel of u bar? If you take any element here, it is of the form v bar of f. So if you take anything v bar of f, we want to show that it is here, right? That means when you apply u bar of v bar of f, we want to show that it is 0. If we can show that, then we are done this. Okay, so for that, let f maps from m double prime to n, because it should be from v bar, right? So f maps from m double prime to n, so v bar of f belongs to image of v bar. Okay, now we will consider what is the u bar of v bar of f, which is same as u bar of v bar f is first of all f composed v, then it is same as f composed v composed u. But if you see this one, because image of u is same as kernel of v, so therefore when you talk about v composed u, it is 0. So f of 0 is 0, you get that this is 0. That shows that image of v bar is contained in kernel of u bar. Okay, now we want to show the other way. That means we want to show that our claim is kernel of u bar is contained in image of v bar. So take an element here, show that it is here. Okay, so start with g belongs to m to n such that g belongs to kernel of u bar. Okay, that means u bar of g is 0, right? U bar of g is 0. That is same as saying that g composed u is 0 map. We have this much information. We want to show that this g actually belongs to image of v bar. That means we want to show that there exists some h such that, of course, such that h such that this g is v bar of h. Okay, but what is meant by saying v bar of h? It's the same as h composed v, right? So we want to find some h maps from m double prime to n. So you can, if you understand this diagram, then it is easy. Proof is very easy. What we have here is given that m to n is already given to us, which is a map g. Okay, and we already have a map v from m to m double prime, right? Then somehow we want to find a h from m double prime to n. So this I will write it in dotted line such that g is equal to h composed v. So g is equal, this is a h, so g is equal to h composed v means this diagram should be commuted. So we want to define this h from m double prime to n such a way that this diagram should commute. That means g is equal to h composed v. Okay, so now how we can define is just tracing this diagram. So you can see here, let me explain. It's not at all difficult. So take this, you take some x here. Okay, somehow we want to get it here. We want to, h of x should be an element here, right? But what we know about v? V is given to be surjective, because our v is surjective. So therefore, if you take any element in codomain here, it has a pre-image. So you can call it, so there exists some y which goes to x, right? So what we have here is v of y is equal to x, right? Now you can send this y to its image. So you can talk about g of y, right? This y I am sending to g of y. We know this belongs to n. So therefore, for this x, we have now, for this x, we can relate this g of y, right? Therefore, how we can define? So define h maps from m double prime to n as h of any x as g of y, where what is relation between y and x? Where this v of y is x. That means this y is nothing but pre-image of x. Okay, is this clear? So this is our h. We have defined this h. Now we want to make sure that this h is well defined. That means it may happen that, what is meant by well defined? It may happen that this x may have, so this given x may have some y1 and y2. Okay, both are going to same x. So at that time we want to make sure that this y1 and y2, their images are also same here. Okay, then we don't have any problem. If g1 and g of y1 and g of y2 are different, then this is not a map. Is that clear? So that is meant by saying well defined. Okay, so assume that y1, okay, so we want to show it is well defined. So v of y1 and v of y2 are equal to x. That means these two are pre-images of x. Then simply you, obviously v of y1 minus y2 is 0, so therefore y1 minus y2 belongs to kernel of v, but kernel of v we know is same as image of u. That is the given condition, right? So therefore y1 minus y2 belongs to image of u. So you can write y1 minus y2 as u of some z, where z belongs to m prime. So y1 is same as y2 plus u of z. So when you go modulo, that means if you take g here, g of y1 equal to g of y2 plus g composed u of z. But g composed u is 0, so therefore g of y1 is equal to g of y2. That means h of x is same. Okay, that shows that h is well defined. Okay, so we have defined h. Now you can easily show that what are all things. H is a well defined map is over. H we want to show it is a homomorphism, that you can easily check. Okay, and this composition is not at all difficult. Okay, this composition is because h of x, you can check, clearly this composition follows, that means commutative follows from this definition itself. H of x is same as this g of y. Okay, g of y, but what we know about x is v of y. So if you write here in place of x, if we write h of v of y is g of y, right? Therefore h composed v is same as g, and that is what we want to show. H composed v is g, right? So that shows that there exists g belongs to there exists h such that g is nothing but v bar of h. Okay, this basic calculations I skip. You can easily check that why it is a homomorphism and so on. Okay, so we have done, we have proved the first part. That means whenever, what we have proved is that whenever you have from m prime to m prime to m double prime to 0 is exact, then we have proved that this, the other one 0 to home to, that is exact. Okay, now assume conversely, suppose assume that this 0 to home m double prime to n, m to n, home m prime to n is exact for all modules n. Okay, we want to show that the map v is surjective. So this is v, right? Where is that? M prime to, yeah, this is u and this is v. This is u, u is m prime to m, and v is m to m prime. What is meant by saying this is exact? So we want to show that this is exact means, so our claim is v is surjective and image of u is same as kernel of this v, right? So we want to show this. What is, how we will show? Obviously v is surjective, we use the fact that v bar is injective. Okay, so v bar is injective means if we know some f such that v bar of f is 0, then we can claim that f is 0. So we want to produce some f such that v bar of f is 0, so that f will become 0, and from there we can conclude that v is surjective. Okay, and we have an option, this n is any a module. So every time we select a suitable n which is an a module, then we will apply this home functor, and we use that it is an exact sequence. Okay, so simply we will define f maps from m double prime to n. Our m this time n is nothing but m double prime to image of v. Okay, so this is the natural map, same x to x bar, which is x plus image of v. Then you can easily check that this v bar of f is 0. Okay, v bar of f is 0, so therefore f has to be 0. If f is 0 means what? F of x, this x should belongs to image of v, right? X should belongs to image of v. That shows that, so this implies v of x, this f is 0, so that is fine. That means f of x is 0, that means x belongs to image of v. But where is x? X is in m double prime. So x is in m double prime, which belongs to image of v, means m double prime is a subset of image of v, but we know image of v is always subset of m double prime, so therefore they have to be equal. That shows that v is actually surjective. Again, the second claim, we want to show that image of u is kernel of v, right? That means we want to show that this and this, right? And what is given is that image of v bar is kernel of u bar. That means this image of v bar is contained here. So when you talk about u bar, composed v bar is 0, right? So that is same as if you take u bar, composed v bar applied on any f is 0. This is same as if you simplify this, f composed v composed u, you get 0, right? But f composed v composed u is 0. So in particular, if you take f identity map, it is true for every f. So in particular, if you take f as identity, right, then what you get is v composed u is 0. So therefore one way, that means image of u is contained in kernel of, image of v is contained in kernel of v. Okay, image of u is contained in kernel of v. That is what we have proved. Now to show the other one, that means our next claim is to show that kernel of v is contained in image of u. Okay, that means take some element here and somehow show that it is here. Okay, so for that, what we define phi, okay, maps from m to n. This time we will take our n as m modulo image of u. Okay, and how every time they are natural maps, send x to x bar, x plus image of u and so on. Then you can talk about kernel of f is same as image of u, right? So therefore, and u bar of phi, if you take u bar of phi is phi composed u, right? but phi composed u of x is equal to, this is same as phi of u of x, but is equal to 0, because what we know is kernel of phi is image of u, right? Okay, so therefore phi bar of u bar of phi is 0, therefore phi belongs to kernel of u bar, right? Kernel of u bar is same as image of v bar, that means phi belongs to image of v bar. If phi belongs to image of v bar means what? There exists a map, okay, belongs to v bar such that v bar of phi is, v bar of phi is this one. Okay, this notation don't confuse, right? That is same as saying that this composed is equal to this, right? That means what we have here is this psi phi, or phi is equal to, you can call it, this is psi composed v, right? That implies you can check that kernel of v is contained in kernel of phi. Why? If we can, from here you can check that kernel of v is contained in kernel of phi, because if v of x is 0, right, then this phi of x is also 0. That shows that this is here, that but kernel of phi is same as image of u, that means kernel of v is contained in image of u, right? Same way the other result you can show it as exercise. I leave it here. 0 to, whenever you have from left exact, okay, then you have here, when you replace this one you have this, right? Okay, the next interesting result, just like how we did tracing these diagrams and so on, we have something called snake lemma. It is an interesting one, so we'll see what is this and how this is constructed and why it is called as snake lemma. So you have 0, so let me write here, 0 to m prime, m prime to m to m double prime to 0. You have an exact sequence, okay, and 0 to n prime to n to n double prime to 0, another exact sequence, and this you call it as u and v. This is u prime and v prime, okay, and you have maps from m prime to n prime, you call it as f prime, and m to n is f, m double prime to n double prime is f double prime, such that this diagram commutes. That means here it is commute, so either you go, so I can write here this is commute and this is also commute, right? That means either you go from m prime to n via m, or m prime to n via n prime, both are equal, okay, fine. So this, when you have such diagram, then there exists an exact sequence. What is that exact sequence? Is if you take f prime, okay, so let me write in another color so that we can understand. So here, if you take m prime is a map from, f prime is a map from m prime to n prime. So if you take kernel of f prime, which is a submodule of m prime, so kernel of f prime, we know this is a submodule of this, right? Then similarly kernel of f we have here, and then this you can call it as u bar, which is a simply inclusive restriction you can call it. Then kernel of f to kernel of f double prime, okay. After that, what we'll have here is, now you take n prime to this f prime is a map from m prime to n prime, so therefore you have a natural map n prime to co-kernel of f prime, co-kernel of f prime. Similarly, you have here co-kernel of f and co-kernel of f double prime, okay. Then 0 we have. Now what we do is we can connect this kernel of f double prime, okay, to co-kernel of f prime. You can call it that as a map D. Okay, this if you want, you call it, this is u bar, u prime bar and v prime bar, okay. And this D, so you can see that this, just like how you have here, is just like a snake, okay. So how these maps are defined, connected, that's maybe the reason it is called as a snake lamp, okay. So let me repeat again. If you have this diagram, commutative diagram with exact sequences, then you always get another exact sequence from kernel f prime to kernel of f to f double prime, then kernel f double prime to co-kernel of f prime, which is called boundary map D. We will discuss how we have defined this then here, okay. So that is this one. So that image I might have not kept here, but I have explained here how this is actually formed, okay. So if you observe here, the getting map from here to here is not a difficult one. From here to here, this you can call it V bar, is not a difficult one. From here to here is not a difficult one here also. What is only major thing is that getting a map from kernel of f double prime, okay, here to co-kernel of f prime, that is called D, and we will see how this D is defined, and remaining all things follows from u, v, u prime, v prime, f prime, f double prime, all those things, okay, which you can one can easily understand just like in previous result, okay. But in this I feel that the main thing need to be discussed is this map D, how we can define D, which is from kernel of f double prime to co-kernel of f prime, okay. Fine. So I'll leave it all those things this in detail I have given here. What we'll do is we'll define how our D is, okay. We'll define D from kernel of f double prime to co-kernel of f prime. You can call it that as a boundary homomorphism, and we'll show maybe one of them, that image of D is kernel of u prime bar, or image of v bar is kernel of D. And the most important thing is defining this map and make sure it is well defined, homomorphism and so on, right? So how we'll do this is again tracing that diagram and so on, right? Okay, so let me write that things here. We can very easily understand. It is just like if you are understood that diagram, and it is very easy, okay. So let me write this m prime to m. So what we have here is 0 to m prime to m double prime to 0. Then we have 0 to n prime to n to n double prime to 0. Okay, what we have here is this is f double prime, right? This is f double prime, and this is f and f prime we have, okay. And here we have kernel of f double prime, okay, right, which is obviously a submodule of this, right? So we want to get an element from here somehow to what we have here is, so let me this one, and from there we want to get co-kernel of f prime. So we should get a map from here to here. So start with an element x belongs to kernel of f double prime. That means what? It is actually an element of, it is an actually an element of m double prime, okay, which is going to 0 here because it belongs to kernel of f double prime. Means what? F double prime of x is 0, okay. So we have an x here which is going to 0 here, okay. Then somehow we should get an element here. If we get an element, you can simply take its natural map. But what are all we know? We know that this is u and this is v, right? So from this you will come here, because this map what we know is a surjective map. So v is surjective, so this x has, so let me write this x has, because this v is surjective, we have a map, so we have an element pre-image, you can call it y, okay. Then this y you can come here, right? So this y, what is meaning of this? V of y is actually equal to x. Now if you come here and you will see that it is going to 0. So this x is going to 0. If you come here and here, it also going to 0. So therefore v of y is equal to x. So you can check that this v prime of f of y is 0. That means this, what is this? This is u prime and this is v prime. So if you can easily check that v prime of f of y, that means you take this y here, so v prime of f of y is actually 0, okay. V prime of f of y. So let me again repeat, it is very interesting and easy to understand if you can follow it. You take x which is going to 0 here, okay. Then because this v is surjective, we know it is a y which has a x, v of y is x, okay. So f double dash x is 0. That means f double dash of v of y is 0 is same as saying that this, because of this commutative diagram, because this is a commutative diagram, so y you take that under this f of y, which will come here and it will go 0 here, okay. So therefore what we got here is v prime of f of y is 0. So f of y, we have some element which is going to 0 here. So that means because this sequence is exact, so you have, So you have f of y here, which is going to 0. So therefore this should come from here because it belongs to kernel. So therefore this is same as image. It comes as image of this u prime. So therefore f v prime of f of y is 0. That means f of y belongs to kernel of v prime, but kernel of v prime is same as image of u prime. So there is some element z. Okay, so there is some element z which is mapping to this f of y. That, so we got an element z. Okay, we got an element, let me write in yellow color. We got an element z, okay, which is actually mapping to f of y, and that is going to 0. So we got some z in n prime such that all this happens. Okay, right? So therefore can you have now an element which belongs to co-kernel of f prime? Simply z bar belongs to co-kernel of f prime. Okay, so that is what our element which we require. This is our z bar we require. Let me repeat again one more time how we are traced and how we got z bar from this diagram one more time. Okay, so take an element, let me write from here. Take an element x, okay, which belongs to kernel of double f double prime. That means what? F double prime of, so that is going to 0 here. But this map is commutative, so x is going to 0 and it is surjective, so you have some y which goes to this, and if you take this one f of y we will get here, this also goes to 0 because this diagram is commutative. Because y going to x, x going to 0, and y going to f of y, so it has to go to 0 because of this diagram is commutative. Now using this left rows is exact, that means f of y is going to 0, so there exists some z which maps to f of y. Now send z to z bar which belongs to co-kernel of this f prime. So we got a map from where to where? X to that means kernel of f double prime. This belongs to kernel of f double prime. So kernel of f double prime to co-kernel of f prime, we got a map. Simply send x to z bar. What? Z bar, how they are all related? In between we have an important element which is y. Okay, so y, v of y is x, and this u prime of z is f of y. So what are all we have? So we can define a map D from kernel of f double prime to co-kernel of f prime. How we can define? Simply take this x, d of x, you define this as z bar, where how x, z bar and all related, where you have a y such that v of y is x, and this z we have in n bar such that u prime of z is equal to f of y. Okay, so if you want this, you can put it f composed v of x. So how this z and x are related? U prime of z is f composed v of x. Okay, fine. Then you can check again. The another thing what we have to make sure is that once we define a map, we want to make sure that this is well defined. So where you want to check if in this entire process, because this x has a pre-image y here, so it may happen that y1 and y2 are two elements which are mapping to same element x. Okay, then we have to make sure that this z, you have z1 bar and z2 bar, they are also same. Okay, that is just like how we define here, and I can skip that, you can go through it, I can quickly explain from here itself. Okay, so just where is that z we have defined, d is well defined, we want to see. Okay, fine. So to show that d is well defined, take y1 and y2 in M which are going to mapping to same element x such that v of y1 is equal to v of y2. So then just like how we did in previous class, it is same as in previous theorem, v of y1 minus y2 is 0. So therefore y1 minus y2 belongs to kernel of v, but we know kernel of v is same as image of u. That means y1 minus y2 can be written as u of z for some z belongs to M prime, right? Okay, therefore again it is same as y1 is equal to y2 plus e of z. Now take f to this one because y1 and y2 belongs to M. So f of y1 is equal to f of y2 plus f composed u of z, right? But this is same as f of u of z, right? F of y1 we know is same as u prime of z1, f of y2 is u prime of z2, and it is this belongs to means it is actually when you go modulo image of f. See, this element what we have here is belongs to image of f, so therefore it becomes 0 when you go to co-kernel. Okay, co-kernel of f, right? So therefore u prime of z1 bar is same as u2 prime of z2 bar, but that is same as, because u prime is injective, this is same as z1 bar is equal to z2 bar, right? Because it is injective, that means you get that z1 bar equal to z2 bar, therefore we got that d is well defined. Okay, now you can easily check that image of v bar is kernel of d, that means it is contained here, and the other part take an element here and show that it is here. This is again just elementary. What you have to know in this entire this is the beautiful beautiness is that how you can trace this diagram. That is the beautiness of this snake lemma. You start here, how you are going here through the commutative diagrams and so on. Okay, so I'll stop here, and in next class we'll see the another concept called like tensor product of modules. Okay, we'll stop here.